So thank you very much. So I am Ruth Mottram. I'm a climate scientist at the Danish Meteorological Institute. And I mostly work in Greenland, or at least I did work in Greenland mostly until quite recently. And so this is a picture from our fieldwork, and I like to think of it as a sort of metaphor for surface mass balance, because it's kind of white and snowy, and you can't really see anything, and you think maybe you're not going to get very much out of this. But with the right guides, in this case our Greenlandic hunters and some very nice dogs, we did actually get some really good results. So I'm going to show a lot of work. Some of it is mine, some of it is my colleagues, a lot of it has come from all sorts of people in the community. I'm sorry if your name should be on here and isn't. It's not intentional, but a lot of people have been working on surface mass balance, and yeah, let's see. Good. Hopefully we all recognize this as a sort of ice sheet model. This is the classic from the 5th assessment report, and it's got all of the components that we're interested in as ice sheet researchers. Snowfall, carving, and I'm only going to sort of talk about this kind of bit that happens at the surface. And it's something that I think has not been, maybe we've paid a lot of attention to it in some ways, but maybe not the right kind of attention. So when we run surface mass balance from models are brilliant. They give you beautiful output and they look fantastic, but we shouldn't necessarily believe everything you see when you look under the bonnet. When we run a model, we take in precipitation. An enormous amount of work has been done in defining surface energy budgets. So we take out the long wave, the short wave, latent and sensible heat. We sum it all up and we say, what's the surface temperature? If it's sufficiently warm to melt, not a big problem in most of Antarctica, but kind of key in a few places. If it's warm enough, then we say, okay, all that heat is being turned into melt. That melt water drips down into the snowpack underneath. If there is a snowpack underneath, that's of course also not always the case. It refreezes, releases latent heat, builds up ice layers. Sometimes if there's ice layers already in there, it can't refreeze and it runs off. And so this is our basic SMB equation. And I would say that for most of the last 15 years or so that I've been working on this, enormous amount of work has gone into this part of it and this part of it. So that is the surface energy balance, getting the albedo schemes better, correct, a lot of work on densification, refreezing, all that stuff. We have paid much less attention to this bit, the precipitation bit, which is actually probably the most key bit in every ice sheet, and this is something that we really need to pay a lot more attention to. That's going to change. Anyway, all of this work, there are now a lot of models. So this was a publication came out last year. We compared 6 different model simulations over the whole of Antarctica. We see a huge spread in estimates of SMB over the continent, integrated over the continent. But we see some hope. There's no significant trend in this. If you take a different starting point, you see a different number here. We see large interannual variability. That's a problem too, actually, because that means that we can't just take 1 or 2 measurements and assume that they're correct everywhere. That means we have to really be careful in time and space. This is all these models are forced with era interim. If you use a different reanalysis, you'll get a different number, especially if you use MIRA, for example, or JRA. One of the other reanalyses will give you probably a different result. Era 5 is relatively close to era interim, but they're also important to understand what's being forced on the boundaries. Lots of things to say about this, but this is just the integrated over the whole continent number. If you look, oh yes, let me just say this. The reviewers in this paper asked us to look at the IMBI number, so this is the IMBI number here. And if we inserted the SMB number from all of these different models into this sort of IMBI number, this is what we get. And so you can see that the Hirham, Racmo, MAR models are all pretty close. Cosmos CLM and MET-UM are down here, a little bit drier than the other models. I don't necessarily, if you look at the results from, for example, MET-UM, which in this case is being run at BAS, and you compare it with weather station data, it's one of the best performing models over the continent. So one of our challenges is to work out how on earth do we assess these models. The spread is large. I would point out that this is the from the Renew data set looking at discharge. It's still the biggest uncertainty. So SMB does have a big uncertainty on it, but it's not the biggest. It's still about discharge from the ice sheet. Of course, that's something that we need to keep an eye on, though, as the climate changes. Yeah, so to bear in mind, I showed the number integrated over the whole continent before. Here is the ensemble mean of all of these numbers. And I think it's really important to bear in mind that these models are putting the snow in different places. So here is MAR and here is RACMO, two very widely used models in Antarctica. MAR has a lot more snow around the Transantarctic mountains and out here, where RACMO is rather dry. We get a bit of a clue from these two Heerham runs. Heerham tends to have a little bit too much snow over the Ronnie ice shelf for whatever reason. These are the same model, exactly the same setup, except this is run at 50 kilometers and this is run at 12-kilometer resolution, and that massively changes where you get your precipitation. Everything has been regridded to the Heerham 12-kilometer grid here, so you get some of this striping as some of that effect. It seems to be a little dry in MET-UM, and Cosmos CLM in this version, it's been upgraded since, was a bit too dry in West Antarctica. So there are definitely, it's really worth bearing in mind that a single model is going to have different biases on a spatial scale. Resolution, as I mentioned, is important. It turns out to be really important also for melt events. Now, obviously, melt events are not a huge concern at the moment, but this is an event on the 15th of January 2016, where we had winds coming through, bringing a sort of firn melting over the Ross ice shelf here. And we can semi-resolve it at 12 kilometers. We don't even see it at 50 kilometers. But if you go down, and this is the satellite-derived belt extent here, if you compare it with Polar Wharf in this case, which was run at 4 kilometers, you get a much better resolution of the melt event over the ice shelf. And that's because you need to go to this resolution to properly resolve the wind speeds. And so the PolarRes project, I've put the logo here, which is paying for my trip, we're setting up non-hydrostatic models specifically to deal with these kind of processes, also to deal with snowfall at high resolution in rough topography. So this is, the next generation is really now getting going, and that's partly driven by both precipitation and melt. I have no idea how I'm doing for time. Am I okay? Okay, good. So I mentioned that there's been a lot of work done on firn models. Over the whole of Antarctica, it doesn't make that much difference. But again, in these areas where we have high precipitation, and especially where we see some melt, having these kind of dense, different firn models does give us quite different results in SMB. So it's definitely worth bearing in mind that we need to have surface processes well resolved if we're looking at SMB over these. And then it's not very clear from here, but one of the big differences between these two is actually spin-up time. And obviously, if you have large areas of the continent with very tiny snowfall rates, you really need to think about your spin-up for your surface mass balance model, because your densification and everything is just going to take forever if you don't. So one of the things we found when we were spinning up this, historically people have used 1 or 2 years and just spun it up over and over again. You really need to use multi-decadal periods, because the internal variability in Antarctica happens on decadal to multi-decadal periods. So if you're using a decade with a persistent positive SAM, for example, it's going to be very different to the average over a long period. This is really to look at, this was a study that was done a few years ago now, an emulation using 3 different regional climate models and 54 different emulations with different firm parameterizations. And the point here is really that the atmospheric forcing is still the biggest single uncertainty in your firn density model. So you can try lots of different things, and places where we know different models are outliers, like this here, MAR seems to have a very different result to the other 2 models. It gives a very different result with firn density up here. It's the same with Heerham. And so different models will really have a different response in different places. So you need to be really careful if you're only using one model. Always try and use an ensemble mean would be my suggestion. I'll skip over that. So let's look at how good these models are. I must admit, the first time we plotted this up, I went, we don't know anything. It's not quite true. We do know something, but it's maybe not what we think we know. So here we have stake measurements from all over Antarctica, observed SMB along the bottom, modeled SMB along the side. Note the logarithmic axes. We tried splitting it out by bin to see if there were any places that we thought were doing particularly well. Some models doing better than others in certain places. Unfortunately, when you look at the statistics, no single model is performing the best in all of these. So they all have their strengths and weaknesses. And you can see that here. I can talk about this later, I guess. The main problem is that our SMB observations are not in the right places. They're not where we want them to be. We miss a lot, and the number of observations is rather small. We don't have a lot of repeat observations, so internal variability starts to become a factor. You don't know if your observation is representative or not. And so filling these gaps is not just a question of, going here and saying, well, we don't have any observations here, let's go and take a few. It's let's go and take a few over a 10-year period, or let's go back every 20 years or something and measure the same place, because that's actually a really important element here, is how does this vary in space and time. However, it turns out that when we were writing that paper, we didn't get all the observations. There are a lot more observations, especially down here, that we just didn't have access to. And this data set came out also last year in ESSD. It's a really nice data set, and we've started to use it now to evaluate the models. It includes a lot more data, including GPR. It's still not enough. You can still see we have some very large gaps, and these are not all observations that are being repeated. So we still need a little bit more, but it's a good start, and this allows us to start doing a bit more rigorous uncertainty estimates. And that's what's here. I don't have time to go into this. It's a little bit complicated, but basically, we can talk about it later if you're interested. We use a piecewise linear function to determine the error estimates based on the size of the SMB. So this is the observed SMB along the bottom in bins, and then compared with different models to see, are there some places? And broadly speaking, the higher the precipitation, the bigger the RMSE, the root mean square error. So, I mean, it's a bit obvious, but if you have more precipitation, it's harder to get it right in a model. And so when we do that, and we recalculated all the errors, and I don't know, Ines has got this data to work with in B3 now. So we're going to try and write this up properly and do it in a more rigorous way. This gives us a much bigger error bar on our SMB estimates than we previously estimated before. But as I say, we have a lot of gaps, and perhaps, maybe more data gives us an even bigger uncertainty. I don't know. Anyway, as I mentioned, so this was largely, these uncertainty estimates were largely determined using stakes. Here we have a very nice study from Brooke Medley et al., where they've taken airborne radar observations, tied them back to fern cores, shallow cores, and it's a really useful way to think about how to evaluate a model, because you get something that is spatially, I forgot to say this actually, but you can sort of see it here. A lot of these observations, so typically we run models over Antarctica about 12 kilometers over the whole of the Pan-Arctic, Antarctic region. One of the problems is you might have a lot of data, but it's in one very small area, maybe even in the same grid point. So it's actually not that helpful for you to be able to evaluate a model over a much wider area, because if you have 100 observations in one grid cell and then a whole bunch of other grid cells with no observations, you're not really any better forward. On the other hand, we also like to know if our one observation in one grid cell is representative of the whole grid cell. So there are very much different scales that we're interested in when we're looking at these things. So there are still large areas that lack SMB data, and getting more radar data, and Alex this morning mentioned KU-band snow radar. I mean, that's something that we haven't really exploited properly, and I think we're just at the start. Again, it comes down to this challenge of the data sets that we're generating now, and how do we best look into them. So I think we're at the start of a journey into using much more remote sensing data to evaluate models and to improve them. So this, I think, has a lot of potential, and I would like to use this more. And so I guess that was the message of this. So these are the key points. We have a lot of mass balance models now, led by different groups. It's a robust ensemble because these models are sufficiently different from each other. We're developing new models with non-hydrostatic physics, prognostic precipitation schemes that we think actually give a much better representation of where the snow is actually falling. Also new processes like drifting snow. So that gives us a robust ensemble, and we're starting to get much better data sets that we can use for robust error estimates. There's still a long way to go before we know exactly what the SMB of Antarctica is, but we're getting there. I think that was it. Yes?
May we have time for a quick question? Anyone has a question?